Hello, physics kids. This is Mr. Hanson coming back at you with another awesome physics video. And this video is dealing with horizontal oscillation. And what you see on my screen right now is a virtual space where you have a little hovercraft over here that's 57 grams, which the grams don't mean anything. And this hovercraft, when I click on it, it will go across here and it will hit the spring. And right now the spring is sitting here in what is called equilibrium, meaning it's not compressed or stretched. And the spring constant is 40.7 newtons per meter. That doesn't mean anything for what we're doing here. This is all qualitative. And this hovercraft is going to hit the spring going at a velocity of 2.4 meters per second. So I would like you just to watch it quickly. Here we go. As you can see, the hovercraft hit the spring, and the instant it hits the spring, it attaches to it, and then it goes back and forth. And it has oscillating motion, meaning it goes back and forth. It has cycles that are evenly timed. All right, I'm going to reset it. Now I want to talk about how it's moving back and forth, and then I'll talk about what we want to do to draw a graph for that. And then we'll further discuss what the graph should look like. So once again, the spring right here is in equilibrium position. When it goes over to here, to its farthest point over here, we'll say that it's at its biggest negative position because negative is left. And then when the spring goes over here, it gets to its biggest positive position because that's right. And so we have positive for right and we have negative for left. And then as it goes across, I want to talk about how it is moving with respect to velocity and then how it's moving with respect to acceleration. And hopefully from that we can figure out how to draw a graph of, not just a graph, a position versus time graph, a velocity versus time graph, and an acceleration versus time graph. And then beyond that, a net force versus time graph, which would actually be exactly the same as an acceleration versus time graph. So here we go, and it hits the spring. It's in equilibrium. And when it hits the spring in equilibrium, that's when the time started. So as you can see, it goes to the left to the big negative position, comes back across equilibrium, and then goes to the right to the biggest positive position, and then goes back through equilibrium. So it's going to the left, through equilibrium to the right, through equilibrium to the left, through equilibrium, and so on and so forth with that oscillating motion. Now let's talk about the velocity as it's going back and forth. So one thing I hope you can see is that the velocity is fastest when it goes through that equilibrium middle position. And it is slowest when it gets to the maximum positions, or the endpoints, if you will. So when it gets here, velocity is 0. When it gets here, velocity is 0. The velocity in the middle is the biggest. Now the velocity going to the left is a negative velocity, and the velocity going to the right is a positive velocity. All right, now let's talk about the acceleration. Now the acceleration in the middle, when the spring is in equilibrium, meaning the spring isn't compressed or isn't stretched, that means the spring at the equilibrium position isn't forcing it either way. And so if there's no forces either way, that's when acceleration is 0. And then when the spring gets fully compressed here at that big negative position, or fully stretched here at the big positive position, that's when the acceleration is the biggest. That's when the spring is stretched out the most or compressed the most, which would mean it has the biggest net force and in turn the biggest acceleration. So now any acceleration pointed to the left is negative and any acceleration pointed to the right is positive. So over at this point here, the spring wants to pull the hovercraft to the right, so that's going to be the biggest positive acceleration. And then over here is where you have the spring wanting to pull the most to the left, and so it's accelerating it most to the left, and so that'd be a biggest negative acceleration. All right, so I hope those words kind of helped you think about how position and velocity and acceleration and even net force are all described throughout that whole oscillating process. So I'm just going to press reset there, and then I want to go to a document I created, and I would actually like you to draw your own, and let me just explain how this graph looks. But as you can see here, I have a position versus time, I have a velocity versus time, and I have an acceleration versus time graph. And I never drew the net force versus time graph, but just know that the net force versus time graph will look exactly like the acceleration versus time graph, because anytime you have a certain net force, you have a certain acceleration, meaning positive net force, positive acceleration, zero net force, zero acceleration, negative net force, negative acceleration, big net force, big acceleration, small net force, small acceleration, so on and so forth. All right, so here's how the graph should look. This is all qualitative, so we don't have numbers, so I have descriptors. And as you can see with the position versus time graph, in the middle here, so this is position on that, I guess you could call it the y-axis. In the middle here, you have a zero position. So that's when the hovercraft is going through that zero position, that equilibrium position, when the spring is not stretched or compressed. And then here you have the biggest positive position, which would be the biggest position to the right. And here you have the biggest negative position, would be the biggest position to the left. And then below here, this would be considered your time axis. And what I have here is a first cycle time, and then I have a second cycle time, and then I have a third cycle time. And so what that means is, for the first cycle time, this is the first time that the hovercraft had went all the way forward and then back to its original position. So that would be the time of one cycle. And then the second cycle time would be the second time it went through a whole cycle going back and forth one full time. And then the third would be the third time it goes back and forth. And so that's the position versus time graph, as you can see. And then the velocity versus time graph set up the same way. You have your first cycle time, second cycle time, and third cycle time, just like on the position graph. But here you have zero velocity in the middle. And then you have the biggest positive velocity, meaning it's going the fastest to the right, and the biggest negative velocity, which means it's going fastest to the left. And then down here you have acceleration versus time, same thing. You have first, second, third cycle times. And then you have the middle at zero acceleration, and then at the top here you have the biggest positive acceleration. So that's when it is accelerating the biggest to the right. And then you have the biggest negative acceleration, so that's when it's accelerating the most to the left. And so from here, you have to draw the various attributes. So position, what is going on with the position of the hovercraft as you start from when the time starts to when it has gone back and forth one time. And then once again, when it's gone back and forth the second time and back and forth the third time. And then do the same thing for the velocity versus time graph and the same thing for the acceleration versus time graph. So what I'd like you to do is try to make a prediction of what those graphs would look like. And then after you are done with that, you can open up the next video to check what your answer should be. Good luck.